Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So we start by calculating the required momentum from de Broglie's relation, which is given by equation 27.78, by which P, or the momentum, is equal to Planck constant over the wavelength. So we solve it to find the momentum. This is the value of Planck constant, and our given wavelength is 4 times 10 to the power minus 12 meter, and we get this value to be 1.658 times 10 to the power minus 22 kg meter per second. Now, in part A, for the proton, we use classical definition of momentum to determine its speed and kinetic energy. So velocity will be equal to momentum over mass of the proton, which will be then equal to, so we use the value of momentum we calculate here, over the mass of the proton, which I have written over here, and this gives the velocity to be 9.93 times 10 to the power 5 meter per second. And we compare it to the speed of light, and we get that this velocity is nearly equal to uh, nearly equal to 0.01 times the speed of light. So our assumption to take the classical definition of momentum is in fact correct or justified. Now then kinetic energy will then be equal to half mv square. So using the kinetic energy we will find the potential difference. So V will then be equal to V, which is the potential difference, will be equal to K over the charge of the electron. This will be then equal to mv square over 2 times E. So we used the kinetic energy expression from here, and this is then equal to mass, which is 1.67 times 10 to the power 27 kg, the velocity, which we found over here, so 9.93 times 10 to the power 5 meter per second, and we take a square, and we have 2 times the charge of electron, and we solve it and we get the potential, which is capital V, potential to be 51 volt. So let's, yeah, to differentiate it from the unit. Yeah. And for the second part, so for the electron, we do the same thing. So we initially assume that this is a classical case, and we find the velocity by doing momentum over mass of the electron. And when we do that, so let's take the value. So we use the same value of momentum that we calculated here, times 10 to the power minus 22 kg meter per second over 1 point, sorry, 9.1 times 10 to the power minus 31 kg, and we get that this velocity is nearly equal to 0.6 c, or 60% of the speed of light. So this velocity is in fact comparable to speed of light. So we need to use the relativistic case here. So we use equation 26.9 to determine the energy now. So unlike this case where kinetic energy is half mv square, so we find the energy first using the relativistic case. So energy will then be equal to Pc whole square plus mc square whole square and the root over of that. So c is the speed of light, m is the mass of electron, p is the momentum we found here. So I'll just save some time writing down the values of each of these variables. So we solve it using all those values and we get the energy to be around 9.95 times 10 to the power minus 14 joules. Now we can find the kinetic energy by subtracting the rest mass energy, which is mc square, from the total energy. So the rest mass energy, so let's just calculate this one at least. So this is the value of total energy minus mass of the electron, which is 9.11 times 10 to the power minus 31 kg. The velocity is 3 into 10 to the power 8 meter per second. And we take a square and find the kinetic energy to be around 1.391 times 10 to the minus 14 joules. Now that we have the kinetic energy, we can find the potential using the same equation as this. So let's write my kinetic energy Ke as I used the same expression over here. So now the potential for the proton will be, then for the electron will be kinetic energy over charge of the electron. So this will be then 3.391 times 10 to the power minus 14 joules over 1.6 times 10 to the power minus 19 coulombs. And note that the charge of the electron and proton is same. They just have opposite sign. The magnitude is same. So that's the reason we use charge of electron over here. So we solve it and we get this potential to be nearly 8,609.25 volt. Or we can say this value to be nearly equal to 87 kilovolt. Okay, so this is the potential. We have the velocity somewhere here, and this is the potential for the proton. So let's write electron over here, and yeah,